In this video, we're going to look at the concept of the formal charge. A formal charge is defined as the charge assigned to an atom in a molecule, assuming the electrons in a chemical bond are shared equally between the atoms regardless of the relative electronegativity. It's kind of like almost like a bookkeeping for the electrons in a molecule. It allows us to kind of keep track of which atom has a certain number of electrons around it, and so therefore how the electrons in a molecule are distributed between the various atoms. But why would we want to calculate a formal charge? What's important about that? Well, being able to calculate a formal charge is important because it allows us to determine which of a molecule's resonance structures is the most stable and therefore the most correct. So sometimes if you have two or three or four resonance structures, one of them is going to be more stable than the others, and so the molecule will resemble that resonance structure more than the other resonance structures. We calculate a formal charge by taking the number of valence electrons in the free atom minus the number of electrons that atom owns when it's in a molecule. And what do we mean by the electrons owned? Well, we say an atom, if it has a lone pair around it in a molecule, then it owns both of those. If it has a bonding pair, then it only owns one of the electrons in the bonding pair. So let's try to clarify this or illustrate this by looking at an example. Determine the formal charges on each atom in a water molecule. If you would, pause the video and give it a try. See if you can figure this one out. Okay, so let's take a look at the steps here. First thing we need to do is draw all of the possible correct electron dot structures or resonance structures. If you're not comfortable drawing electron dot structures and resonance structures, please review those videos and the chapters in your textbook before continuing. So for water, we can only draw one correct dot structure, and you can see that here. The second step, determine the number of valence electrons for each of the atoms as if they were free atoms. In other words, oxygen is in group 6, and so oxygen has 6 valence electrons. Hydrogen is in group 1, and it has 1 valence electrons. You can also see this if you draw out the electron configurations for oxygen or hydrogen. The third step, determine the number of electrons each atom owns in this molecule. How do we do that? Well, we mentioned it before. If an atom has a lone pair around it, then it owns both of those electrons. If it has a bonding pair, so it's sharing those electrons, then it technically owns only one of those electrons. Now again, this is not really what happens inside the molecule, but we can use this terminology or these definitions when we're calculating a formal charge. So this applies only to calculating formal charges. So let's take a look at oxygen. Oxygen has one lone pair around it, so it owns both of those, and it has another lone pair, so it owns both of those. So oxygen owns 1, 2, 3, 4. Then it has a bonding pair. It only owns one of those bonding electrons, and then it has another bonding pair. It owns only one of those. So oxygen has 1, 2, 3, 4, 5, 6. It owns 6 electrons. Hydrogen, of course, it has no lone pairs and only one bonding pair. So hydrogen owns only one of those electrons, as does this hydrogen. So I only have one hydrogen here, but this applies to both of those. So our fourth step, subtract the electrons owned by an atom from the number of valence electrons it has if it was a free atom. So for oxygen, we said it has 6 valence electrons in the free atom, and it owns 6 electrons in this molecule. So its formal charge would be 0. Hydrogen has a 1 valence electron, and each of our hydrogens owns 1 electron, so it has a 0 formal charge as well. So this oxygen has a 0 formal charge, this hydrogen has a 0 formal charge, and this hydrogen has a 0 formal charge. So we calculate the formal charge for each atom in the molecule. So we wouldn't say that the molecule has a formal charge. Instead, we talk about the formal charge for each atom in the molecule. So we said that we could use formal charges to determine which of a molecule's resonance structures is the most stable and therefore the most correct. Well, how do we do that? Well, first thing we do is we draw the resonance structures, and then we calculate the formal charge for each atom in all the different resonance structures. So when you have multiple options or multiple resonance structures, the resonance structures where each atom has the lowest formal charge is the more stable. So if one resonance structure, all the atoms have 0 formal charges, and another resonance structure for the same molecule has formal charges of, say, +1 and -1, the resonance structure where everything has a 0 formal charge is going to be the more stable. Now, if there's two resonance structures or more resonance structures where none of the atoms have all 0 formal charges, then we need to look at the electronegativity. The negative formal charge should be on the more electronegative atom. So a negative formal charge is more stable when it's on a more electronegative atom, and consequently the more positive formal charge is more stable when it's on the less electronegative atom. So let's look at a couple of examples to illustrate this. Determine the most stable resonance structure for carbon dioxide. Pause the video, draw the different resonance structures that exist, and then see if you can figure out which one is the most stable. Pause the video and give that a try, please. Okay, so first thing, let's draw the resonance structures for carbon dioxide. So you can see those 3 structures here. Next thing, we need to calculate the formal charge on each atom in each of our resonance structures. So let's look at this first resonance structure. Our first oxygen has 6 valence electrons. Oxygen always has 6. And this oxygen owns 1, 2, 3, 4, 5. So this oxygen, the first oxygen that we see here, has a +1 formal charge. Our carbon has 4 valence, and it owns 1, 2, 3, 4. And so 4 minus 4 is 0. So the carbon has a 0 formal charge. Our other oxygen has, again, 6 valence electrons, and this oxygen owns 1, 2, 3, 4, 5, 6 from the lone pairs, and 1 from the bonding pair, so a total of 7. 6 minus 7, this oxygen has a -1 formal charge. Let's look at our second carbon dioxide resonance structure. Our first oxygen has 6 valence, and it owns 1, 2, 3, 4 from the lone pairs, 5, 6 from the bonding pairs. 6 minus 6, this oxygen has a 0 formal charge. Our carbon, again, 4 valence. It owns 1, 2, 3, 4. So this carbon has a 0 formal charge. And this oxygen is identical to the other oxygen, so we can say it also has a 0 formal charge. And lastly, our last valence resonance structure, this oxygen has 6 valence and owns 7. So this oxygen has a -1 formal charge. Our carbon, again, has a 0 formal charge. And this oxygen has 6 valence and it owns 1, 2, 3, 4, 5. So it has a +1 formal charge. So the first resonance structure and the third resonance structure, those are equally stable because they have the same numbers of formal charges. Our middle resonance structure, though, is the most stable because all of the atoms have a 0 formal charge. So carbon dioxide is going to resemble this resonance structure because this is the most correct resonance structure of the 3. Let's try one more. Pause the video and see if you can determine the most stable resonance structure for the thiocyanate ion. So pause the video and give it a try. Okay. So first, let's draw the resonance structures for thiocyanate. You can see we have those here. And now we calculate the formal charge for each atom in each of our resonance structures. So here, the first one, our sulfur, 6 valence, and it owns 7, so the sulfur has a -1 formal charge. My carbon, 4 valence, and it owns 4, so 0. The nitrogen has 5 valence, and it owns 1, 2, 3, 4, 5, so it has a 0 formal charge. Also notice that the formal charges add up to the charge in the overall molecule. So that's one way you can check your work. The formal charges should always add up to the charge on the molecule. And if the charge is 0, then of course they add up to 0. For our second resonance structure, you can see our sulfur owns 6, and it has 6 valence, so it has a 0. Our carbon has a 0 formal charge, and the nitrogen is in group 5, and it owns 1, 2, 3, 4, 5, 6, so the nitrogen in this resonance structure is a -1. Again, they all add up to -1. And lastly, we have our sulfur, group 6, and it owns 5, so our sulfur has a +1 formal charge. The carbon has a 0 formal charge, and the nitrogen here, 1, 2, 3, 4, 5, 6, 7, it owns 7, and it has 5 valence. 5 minus 7 gives us a -2. Again, they add up to 0. Okay? So in the first two, only one of the atoms has a formal charge, the other two have a 0 formal charge. In this structure, 2 of the atoms have a formal charge, and only one of them is 0. So we can eliminate this third resonance structure. It's not going to be the most stable because the atoms all have more formal charges than in the first two. However, these two, we might want to say, oh, those are equally stable, but let's look. Nitrogen is more electronegative than sulfur. Remember our second rule. The negative formal charge is more stable when it's on the more negative or more electronegative atom. So the negative formal charge is more stable when it's on the nitrogen. And so our middle resonance structure is going to be the most stable. So the thiocyanate ion will resemble more closely this middle resonance structure. So review those a little more and be sure you understand the terms and can predict the more stable resonance structure using formal charges.